Thank you, Katharina. Hello, all. I'm your host, Colin Rude, and I'm stoked to share with you the applications of this research. The porous media that was modeled was known as a flat dialyzer plate, which is a semi-permeable membrane that excels in separating blood and dialysate. Here you see a diagram of the process for dialysis. It is first pumped out of the body and then it goes through a filter followed by an air trap before it returns to the body. The part that these results apply to is the dialyzer filter. Traditionally, dialysis uses hollow fiber technology, which requires a long flow path and higher blood flow rate and has limitations for home dialysis. Flat plates can be more suitable for home dialysis due to their potentially lower blood flow requirements and more compact design. Naturally, the next step from home dialysis is artificial kidneys. In a normal kidney, there are these filtering units called nephrons, and in these filters, there's something called a glomerulus, which selectively filters out wastes and fluids from the bloodstream while not letting larger things like proteins or blood cells through. This method is known as ultrafiltration. The glomeruli make up a total surface area of 0.6 meters squared. Now, there are over 1 million of these in the actual kidney, but artificial kidneys aim to recreate the surface area using the flat dialyzer plates that mimic the function of glomeruli so that an artificial kidney could filter a similar amount of blood. Flat dialyzer plates are the focus of this research paper, whose model consists of multiple compartments made out of 2 layers of cellulose. The goal of this paper is to see how the results for ultrafiltration rate and mean pressure difference compare to experimental studies. For the cellulose membrane, the ultrafiltration rate QA can be calculated by taking the difference between the flow rates on each side of the membrane as seen in the equation on the screen. This is important because it tells us how effectively the membrane is filtering out waste. We substitute in the values of x equals 0 and x equals L in the axial flow rate equation to get the ultrafiltration rate QA, as you can see in the bottom equation on the screen. The drop in pressure can be calculated using the mean value pressure difference equation at x equals 0 and x equals L, which leads to the equation at the bottom of the screen. We can see the numerical results of this model presented in a table that is now on the screen. The results from this study are boxed in red at the bottom, with all the results from experimental studies above that. On the left, we have the membrane filtration coefficient, and on the right we have the mean pressure difference. As you can see, the results from this study are very similar to the results from previous experimental studies. To find the parameters, data can be used from the experimental results to calculate a numerical value for the ultrafiltration. The equation on the screen shows what that looks like. QA can be linearized when this term right here on the screen is much less than 1, leaving us with this equation at the bottom. This shows an independence of the ultrafiltration rate with the axial flow rate Q. This also means the ultrafiltration rate is a linear function, or that has been stated experimentally in previous studies. If the value of eta is close to 1, then our axial flow rate is roughly this. According to this equation, the axial flow rate is decaying exponentially with decreasing value of x, and the result matches previous experimental derivations.